Welcome to today's paper reading. Today's paper is titled, ImageBind-LLM, Multi-modality Instruction Tuning. This paper was published on AR14 by Jiaming and colleagues from Shanghai Artificial Intelligence Laboratory, CUHK-MM Lab, and Vivo AI Lab. ImageBind-LLM is a novel approach to multimodality instruction tuning for large language models. Unlike previous methods that focus on language and image instruction tuning, ImageBind-LLM can handle a variety of modalities including audio, 3D point clouds, and video. During training, a learnable bind network is used to align the embedding space between LLaMA and ImageBind's image encoder. This alignment allows visual instructions to be progressively injected into the model via a gating mechanism. At inference time, multimodality inputs are processed by a visual cache model, which helps to enhance cross-modal embeddings and mitigate discrepancies between training and inference modalities. The ImageBind-LLM model is designed to handle a wide range of input modalities, including images, text, audio, 3D point clouds, and video. This is achieved through the use of specialized encoders like ImageBind and PointBind, which facilitate the encoding of these diverse inputs into a unified embedding space. During the training process, the image encoder from ImageBind is kept frozen, while other parts of the model are fine-tuned using parameter-efficient techniques such as LoRa and bias norm tuning. This approach not only enhances the model's efficiency but also ensures that the original language knowledge within LLaMA is preserved. Additionally, the model employs an attention-free injection method, which simplifies the process of integrating multimodality conditions into the language model by using a learnable gating mechanism. This method allows for a more straightforward and effective way to inject new knowledge into the model as it trains. Figure 1 contrasts traditional visual instruction models with our proposed multimodality ImageBind-LLM. Traditional models, as depicted in A, are limited to image-based instructions. In contrast, our ImageBind-LLM, shown in B, is designed to handle a broader range of modalities including text, audio, video, and 3D point clouds. This expansion allows ImageBind-LLM to provide more comprehensive and versatile instruction following capabilities, demonstrating its potential for broader applications and improved performance across diverse input types. In the realm of visual instruction models, LLaMA Adapter introduced the concept of generating language responses based on image inputs. More advanced models like BLIP2, LLaMA, and Mini-GPT-4 have since been developed to produce high-quality vision language data. Video LLM and Video LLaMA extend this capability to video instruction following. On the topic of multimodality alignment, models such as CLIP, Align, and Florence use contrastive learning to align image and text pairs. Flamingo, BLIP2, and Magic employ intermediate networks to connect vision and language encoders. AudioClip and PointClip extend the embedding space to include audio and 3D point clouds. Our ImageBind-LLM advances this field by tuning a multimodality LLM with attention-free zero-initialized injection and cross-modality cache retrieval, enabling widespread applications across various modalities. In this section, we first revisit prior works including ImageBind, LLaMA Adapter, and cache models. ImageBind connects different modalities through a single joined embedding space, while LLaMA Adapter focuses on parameter-efficient fine-tuning. Cache models store features and labels for efficient retrieval during inference. We then introduce ImageBind-LLM, which involves vision language pre-training, multimodality instruction tuning, and cache retrieval for enhanced inference. Finally, we discuss advanced applications such as bilingual instruction tuning, any-to-any generation, and integration with object detection. Figure 2 illustrates the training paradigm of ImageBind-LLM. It highlights the use of the joined embedding space in ImageBind, 12, for multimodality instruction tuning of LLaMA, 11. The figure shows the process of leveraging image-text datasets for this purpose. Additionally, it introduces a bind network for embedding alignment and an attention-free zero-initialized mechanism for injecting visual knowledge into the model. This approach ensures that the model can efficiently incorporate multimodal data without the complexity of attention layers. Figure 3 illustrates the detailed architecture of the bind network, which is designed to align the embedding space between ImageBind and LLaMA. The bind network employs cascaded blocks consisting of RMS norm, CLU activation functions, and residual connections, all inspired by the feed-forward network, FFN, in LLaMA. A linear projection layer with a weight matrix W0 is used to transform the CI-dimensional global image feature encoded by ImageBind into a form compatible with LLaMA's feature dimension. Additionally, the attention-free zero-initialized injection method is utilized, which involves a learnable gating factor initialized by 0, denoted as 0, to control the level of integration between the image feature and word tokens in LLaMA. Figure 4 illustrates the process of cache retrieval for inference in ImageBind-LLM. The primary objective is to mitigate the discrepancy between training and inference by constructing a training-free visual cached model of ImageBind-encoded image features. During inference, the model enhances multimodality embeddings by retrieving the top-case similar visual features from the cache model. This approach ensures that the model can adaptively incorporate similar visual semantics from the cache, thereby boosting the representation quality of other modalities and reducing the semantic gap to the images used for training. In this section, we present the quantitative and qualitative evaluation of ImageBind-LLM. The model was quantitatively evaluated on 27 datasets using a zero-shot approach, covering tasks such as optical character recognition, OCR, key information extraction, KIE, image captioning, visual question answering, VQA, and knowledge-grounded image description, KGID. ImageBind-LLM demonstrated competitive performance compared to other vision language models, VLMs. Additionally, we evaluated the model on the newly proposed MME benchmark, which measures multimodality capabilities in perception and cognition tasks. ImageBind-LLM performed competitively in these tasks as well. Qualitatively, we analyzed the model's ability to understand and generate responses across multiple modalities, its integration with Stable Diffusion for generating detailed image responses, and its advanced applications, including API control for various visual tasks. Figure 5 presents the multimodal captioning results generated by ImageBind-LLM. The model is trained on a dataset consisting of image-text pairs, enabling it to produce modality-specific outputs for images, audio, video, and point clouds. The training focuses solely on the parameters of the bind network, allowing ImageBind-LLM to connect other modalities with language models without additional retraining. While the model may not generate lengthy, detailed descriptions, the foundational capabilities developed during this stage are crucial for subsequent instruction tuning. Figure 6 showcases the versatility of ImageBind-LLM in handling multimodal instructions across various types of inputs. The figure includes examples where the model is instructed to describe an image, write a poem based on an audio clip, introduce a movie, and describe 3D objects from point clouds. Each example demonstrates the model's ability to generate detailed and creative outputs, reflecting its capacity to understand and respond to diverse modalities without the need for retraining. This capability is crucial for enhancing the model's instruction-following abilities in a multimodal context. Figure 7 illustrates the integration of various modalities with ImageBind-LLM, showcasing its ability to process and generate detailed responses from image, audio, and point cloud inputs. The figure highlights the model's capability to produce rich, multimodal outputs that capture the essence and details of the input data. Additionally, it emphasizes the potential for further improvement by integrating domain-specific knowledge through modality experts, thereby enhancing the model's understanding and response quality in specialized contexts. Figure 8 showcases the advanced capabilities of the bilingual ImageBind-LLM and its integration with Stable Diffusion. The bilingual model demonstrates its ability to generate accurate Chinese responses to Chinese instructions, highlighting its emerging capacity in handling Chinese visual instructions. Additionally, the integration with Stable Diffusion enables the model to produce detailed image responses from various inputs such as images, audio, and point clouds. This dual functionality underscores the model's versatility in both language and image generation tasks, providing a comprehensive understanding of multimodal inputs. Figure 9 illustrates advanced examples of integrating ImageBind-LLM with modality experts to enhance its multimodality understanding capacity. The use of a speech-to-text expert provides context to improve the model's audio understanding. Additionally, class labels extracted by a video object detector help the model catch details of video clips. By cascading ImageBind-LLM with object detectors, the reliability of multimodal LLMs is improved through better text-object association. Figure 10 showcases advanced examples where ImageBind-LLM is cascaded with object detectors. This integration allows the model to associate text responses with specific objects in the image, thereby enhancing the reliability of multimodal large language models, LLMs. The figure demonstrates how this combination improves the model's ability to reason and provide accurate descriptions based on visual inputs, making it a powerful tool for tasks requiring both visual and textual understanding. Figure 11 showcases the advanced capabilities of ImageBind-LLM as a chatbot. It highlights the model's ability to comprehend and reason with multimodal content in response to user queries. This makes ImageBind-LLM a strong candidate for a multimodality chatbot, capable of impressive visual understanding and multimodal conversation skills. The figure demonstrates how ImageBind-LLM can effectively handle complex interactions involving images, audio, and text, showcasing its potential in real-world applications. Figure 12 showcases the advanced capabilities of ImageBind-LLM in handling various visual tasks through API control. The figure demonstrates the model's proficiency in tasks such as object detection and image editing by effectively employing different APIs. This highlights the potential of ImageBind-LLM in multimodal tool usage, making it a viable candidate for complex visual task automation. Figure 13 illustrates the failure cases of ImageBind-LLM, highlighting its tendency to describe objects not shown in the image, which is attributed to the model's limited visual token injection and sensitivity to modality mixing ratios. This figure serves as a critical example of the model's challenges in accurately interpreting multimodal inputs, particularly when mixing different concepts like sky images and dog barking audio. Table 1 presents the zero-shot performance of various models on optical character recognition, OCR, key information extraction, KIE, and image captioning tasks. The evaluation metrics used include word accuracy for OCR datasets, entity-level F1 score for KIE datasets, and CIDR score for image captioning datasets. Notably, ImageBind-LLM, which is ImageBind-LLM trained on multi-turn conversation data, is also included in the comparison. The table provides a comprehensive view of how each model performs across these tasks, highlighting the strengths and weaknesses in their zero-shot capabilities. Table 2 presents the zero-shot performance of various models on visual question answering, VQA, knowledge graph image description, KGID, and visual entailment, V, tasks. The VQA tasks include DocVQA, TextVQA, SDVQA, OCRVQA, OKVQA, GQA, VisDial, IconQA, and VSR. For KGID tasks, the performance is evaluated on ScienceQA and VisWiz benchmarks. The evaluation metrics used are mean reciprocal rank, MRR, for the VisDial task and top 1 accuracy for the remaining tasks. This table provides a comprehensive view of how different models perform in these tasks without prior training on the specific datasets. Table 3 presents a detailed comparison of perception performance across various models on the MME benchmark. The benchmark evaluates models on 10 subtasks, each contributing 200 points to the overall perception score, which totals 2,000. Notably, ImageBind-LLM demonstrates superior performance in the existence and artwork subtasks, outperforming other models in these categories. This table provides a comprehensive view of how different models handle perception tasks, highlighting ImageBind-LLM's strengths in specific areas. Table 4 presents a comparison of cognition performance across various models on the MME benchmark. The benchmark evaluates models on 4 subtasks: common sense reasoning, numerical calculation, text translation, and code reasoning. The full score for the overall cognition tasks is 800, with each of the 4 subtasks contributing a maximum of 200 points. The models included in the comparison are Mini-GPT-4, Otter, LLaMA Adapter, LLaMA, PandaGPT, and ImageBind-LLM. The table provides detailed scores for each model across the subtasks, offering insights into their relative strengths and weaknesses in cognitive tasks. In this work, the authors propose ImageBind-LLM, a multimodality instruction model that integrates image, audio, 3D point clouds, and video into a single large language model. This is achieved by aligning ImageBind's visual encoder with a language model through a learnable bind network. The model allows for training-free inference by directly feeding multimodality inputs into ImageBind-LLM without the need for additional training. To address modality discrepancies, a training-free image cache model is introduced. The performance of ImageBind-LLM is evaluated across 27 traditional vision language datasets and a new multimodal benchmark, ME, where it demonstrates comparable performance to recent multimodal large language models. The authors also provide qualitative analysis to showcase ImageBind-LLM's multimodality understanding capabilities. Thank you for watching.